Take a look at this. What you're seeing here is a classic industrial boiler house. For so many process plants, this is the absolute heart of the operation. And it's all designed for one single critical job, to generate huge amounts of high-energy steam. So let's get right into it and unpack why this equipment is so important.
So, why steam? Of all the ways to move energy around a plant, why is steam the undisputed king? Well, it all comes down to its unique physical properties. It can hold an incredible amount of energy, over 1,000 BTUs per pound. But here's the real kicker. Most of that energy isn't temperature you can feel. It's stored as what we call latent heat. This allows it to deliver a massive energy punch, all while staying at a perfectly constant temperature.
All right, to really get how this works, we're going to follow the path of energy right through this cutaway. This is a super common design, a 3-pass Scotch Marine fire tube boiler. You see these things everywhere. In this view, it just perfectly lays out its entire internal design. So let's follow the flow.
Everything, and I mean everything, starts right here at the burner. This is where your fuel, say natural gas, gets mixed with just the right amount of air and, boom, it's ignited. This is our first major energy conversion. We're taking the chemical energy that's locked inside the fuel and instantly turning it into pure thermal energy, a powerful, roaring flame.
Now that flame gets shot right down this huge central tube. We call this the furnace, and it's the first pass. This is where the heaviest lifting happens in terms of heat transfer. The energy radiates out from that intense flame, blasts through the tube wall, and starts heating the water that's surrounding it.
But we're not done yet. There's still a ton of usable energy left in those hot combustion gases. So when they hit the end of the furnace, they do a complete 180 and travel back through these smaller bundles of tubes. That's our second pass. Then, believe it or not, they do another 180 for a third pass before they finally head out the stack. This winding path is all about maximizing the surface area to squeeze every last bit of heat out of those gases through convection.
Okay, so as the water on the other side of these tubes keeps absorbing all this heat, its temperature climbs right up to the boiling point. And this is where the real magic happens. The water turns from a liquid into a gas, into steam. That phase change absorbs a colossal amount of energy, not as temperature, but as that latent heat of vaporization we talked about. It's like charging a massive energy battery. Now, what we've just seen brings up a really key distinction in boiler design. In the fire tube boiler, the hot gas is inside the tubes and the water is outside. A water tube boiler flips that completely. The water is inside the tubes and the hot gas surrounds them. So why the two designs? Well, fire tube boilers are fantastic for lower pressures, usually under 300 psi. But if you need insane pressures, think over 3,000 psi for power plants or massive refineries, you have to go with a water tube design.
But here's a catch. You can't just keep boiling the same water indefinitely. Think about it. When pure steam leaves the boiler, it leaves behind all the minerals and junk that were dissolved in the water. This stuff gets more and more concentrated. We call this total dissolved solids, or TDS. If your TDS gets too high, you get two big problems. Scale, which is like a rock-hard insulation on your tubes that kills your efficiency, or foaming, which can carry water over into your steam lines. Managing TDS with a process called blowdown is an absolutely critical part of running a boiler.
So, where do we put all this beautiful steam to work? Here's a textbook application: heating a jacketed chemical reactor. For a sensitive batch reaction, your #1 goal is precise temperature control. Steam is perfect for this. Why? Because it condenses at a constant temperature, delivering perfectly uniform heat all around the vessel. You don't get any hot spots that could potentially scorch your product and ruin the whole batch.
Now let's look at a totally different application, a paper mill. The goal here isn't finesse, it's brute force. We're talking about bulk water removal on a massive scale. When a paper web is formed, it's almost all water. So they run it over these gigantic steam-heated rolls that run 24/7. This is all about leveraging steam's incredible energy density to evaporate tons and tons of water every single hour. But for systems this big to run safely, you better know what to do when things go wrong.
Okay, let's put on our plant engineer hat. You get a call from the control room. The boiler water level is bouncing all over the place. This is a classic and potentially dangerous symptom we call swell and shrink. A sudden drop in steam demand can cause the pressure inside to spike, collapsing steam bubbles and making the level look like it's plummeting. A big increase in demand does the exact opposite. So what do? How do you start troubleshooting?
You always start with the data. First thing, you look at the steam flow meter. Are the swings in the water level happening at the exact same time as big changes in steam flow? Is some big user downstream suddenly slamming a valve open or shut? Next, you check the level transmitter itself to make sure its signal is clean. Only after you've checked the data do you start checking the hardware. You might ask an operator to stroke the feedwater control valve from the console, confirming it moves smoothly and that its position feedback actually matches what the controller is telling it to do. It's all about a calm, systematic process of elimination.
And that brings us to a really important point. A boiler is never an island. Its health and reliability are completely dependent on the system feeding it. What you're looking at here is a deaerator. Its main job is to use a little bit of steam to preheat the incoming feed water. But, even more importantly, it strips out dissolved gases, especially oxygen, which is incredibly corrosive to steel at boiler temperature.
So, let's wrap up with this thought. Everybody, and I mean everybody, is focused on boiler efficiency. And yeah, it's really important. But the long-term life of that asset, its integrity, that often begins right here in the feedwater system. A well-operated deaerator is your absolute first and best line of defense against internal corrosion and the damage from thermal shock. It's a great reminder that to truly understand any single piece of equipment, you really have to understand the entire system that it's a part of.